Welcome to a demonstration of using ADS to design a power detector and antenna for a passive RFID tag. RFID systems include readers or interrogators and passive or active tags or transponders. Considerable attention is paid to passive tag design to achieve very low cost per tag. This demonstration will focus on some aspects of passive RFID tag design. Passive tags for RFID obtain power from RF energy transmitted by the reader or interrogator using a detector circuit. The antenna load is modulated by the transponder IC to send information to the reader via backscatter. Critical areas for design include obtaining a good match to the antenna and finding an efficient detector circuit. To achieve our goals, we will follow this design flow. First, we will determine the output voltage characteristic for one diode and again for two diodes in a voltage doubler configuration. Next, we design a patch antenna using momentum and export it to the schematic using the Advanced Model Composer, which allows for tuning and optimization without further electromagnetic simulation being required. Finally, using ADS, the antenna is matched to the circuit and optimized. To design our RFID detector, let's begin with a single diode circuit. Using a model for an Agilent Schottky diode and matching it to a power source using the Design Guide Smith chart utility, and finally adding an output capacitor and load resistor, we can determine the output voltage as a function of input power. The detector has a square law characteristic at low power levels with the output voltage proportional to input power, or voltage squared. At higher input levels, it becomes more linear. Next, we'll reconfigure the detector circuit as a doubler. We also can place a probe point to observe the voltage between the two diodes. To understand the performance of the voltage doubler, let's superimpose its performance over the output voltage versus input power for the single diode detector, as shown here in the red trace. The blue trace represents the dividing point between the two diodes. The green trace represents the doubler's output. Above -10 dBm, it exceeds the output voltage for the single diode and approaches 1 volt at just over 0 dBm. Now that we have designed the detector, the next step is to design and integrate the antenna. Using momentum, a patch antenna is designed and tuned to the desired operating frequency of 915 MHz. The design is exported to ADS using the Advanced Model Composer. The parameter DS1 is the depth of the feed line into the patch. By varying DS1, we can control the input impedance of the antenna without significantly changing the center frequency. And, since we are using the Advanced Model Composer, we don't need to run additional electromagnetic simulations. To complete the design, we'll integrate the layout component generated by the Advanced Model Composer into the detector circuit. The parameter DS1 is available to allow us to tune or optimize the antenna's feed point. To tune the parameter, we'll enable the tune mode and select the parameter. Then we can tune it for maximum output voltage. We'll begin by setting DS1 to 22 millimeters. Now we'll tune it to 18 millimeters, and finally to 12 millimeters. We can see that we found a setting that provides maximum output voltage. Let's review the benefits of RFID tag design using ADS and momentum. The Advanced Model Composer, or AMC, exports antenna simulation data and a placeable layout component from momentum to ADS. This model may include a parameter that varies the antenna's geometry, simplifying the design process and enabling tuning and optimization without requiring additional EM simulation. The optimum match is obtained by connecting this component to the detector circuit in ADS and tuning or optimizing. Thanks for watching this Agilent ESOF EDA demo, and we hope you're successful using ADS to create your RFID designs. Please also view the Advanced Model Composer demonstration and our other demos on the web.